and welcome to your only lesson before our next class. So we've been doing a lot of graphing and looking at key features, specifically um, these sort of key features, these characteristics, and we've been practicing understanding what we mean by domain range, the increasing and decreasing intervals, positive, negative intervals, and then we also talked about rate of change. But in the end, graphs are supposed to have a purpose. And that purpose, believe it or not, is to make people's lives easier. Think about how the coronavirus is going, guys. When you always wonder, like, how many people have the coronavirus and people have died, and like which states are suffering. You can like easily just Google that, look at a graph, and it's way better than a bunch of numbers, right? You can just tell based on how the graph looks. So what we're going to do today is practice creating graphs from different situations. In fact, we're just going to do it for two situations. Speaking of diseases and the coronavirus, we can go ahead and have our first example of what I mean by this to be about something called measles. Um, I was going to show you guys what measles look like, but then it honestly looks really disgusting, so Google that at your own risk. These examples right here are going to be from this example is going to be from page 19, example B in your book. You might want to take out volume 1 of your book, pause this video, get that out, and then we're going to start with this. So if we look at page 19B from our book, let's actually try to organize this a little bit better. It looks like this right here. If you take a look at all this information, this whole thing's asking us to, if you look at the very bottom, to sketch a graph of the function for the incidence of measles. We take a look at our graph right here. The x-axis represents years since 1974. So at 0, that means we're going to start in 1974. And then each of these numbers right here represents cases per 100,000 people. So for every 100,000 people, I put a dot right here. For every 100,000 people, 5 of them would have measles, so on and so forth. Well, we notice that the part of the problem says the incidence of measles in the United States in 1974 was about 10 cases per 100,000 people. So on my graph, I'm going to want to put down a nice dot at 10. So what I'm going to do is I'm going to read the rest of the situation involving measles as time goes on, but instead of like actually drawing the graph, I'm only going to put down specific key points. So we know we're starting at 10. And then it says from 1974 to 1980, there were drastic fluctuations in the incidence of measles in the United States. That doesn't really tell us so much. Let's just move on. Then we read, in 1975, there was a slight increase in incidence from 1974. So 1975 is just 1 year after 1974. It doesn't really tell us a specific number, but we know that whatever the dot we're going to put on this graph, it should be a little bit above 10. So after 1 year, we know it's going to be a little bit above 10. Is that 100% accurate? Well, based off this information, we can't do much more. So let's keep reading. This says right here, the next 2 years saw a substantial increase in the incidence, which reached a maximum in 1977 of about 26 cases per 100,000 years. 26 is the highest this graph's going to get, maximum. Now, if this last dot we put down was 1975, and it said next 2 years, so I'd go all the way to the 3 mark, and we know it's going to be 26 cases, so I'm going to put a dot right all the way up here. See that? So notice that's 2 years after the blue mark, because that's 1975, and it goes all the way up to 1977. Notice how I'm not even bothering connecting these dots yet? Let's leave that to the end, guys. So let's keep reading. From 1977 to 1979, the incidence fell to about 5 cases. So once I get to 2 more years, I should go all the way down to 5 right here. Okay, that's a huge drop. Good, good. Measles are pretty terrifying. But notice it says afterwards, the incidence fell much faster from 1977 to 1978 than from 1978 to 1979. So it says right here, if this is 1977, the green dot was 1977, 3 years after 1974. It says it dropped a lot quicker in the first year than in the second year. And they don't really tell us where. So I'm just going to put a dot right here. Notice how from green to purple, it dropped a lot. And then from purple to yellow, it only dropped a little bit. Because that's what it tells us, right? It says from 77 to 78, it drops a lot. And then from 78 to 79, it drops, but not as much. And the last part says, Finally, from 1979 to 1980, that's going to be one more year, right? Because 5 plus 74 is going to be 79. The incident stayed about the same. That means my last dot is going to be right here. So now I have all these dots, and all I'm going to do is connect the dots from here to here, from here to here, from here to here, from here to here, and here to here. So notice this follows the story of what we just did, where it went up by a little bit for a year, and then it jumped all the way up here, and then it went down, down, and then it leveled off. Now, notice how I handled this problem, guys, is I dealt with one situation at a time. That's exactly what you need to do. If you look at this as one big paragraph, of course it's going to be overwhelming and crazy. Let's do one more problem. Let's do something a bit healthier than measles. Let's talk about strawberries at a grocery store. So once again, we take a look at this graph that we're supposed to be sketching. The bottom of the x-axis represents hours, and the y-axis represents cartons of strawberries. So we're going to read this word problem step by step. A grocery store stocks shelves with 100 cartons of strawberries before the store opens. So at the 0 mark, before it opens, we know we can put a dot at 100. And just because they already gave us this graph, we can already assume that this graph isn't going to go much higher, right? It's going to go lower. We can't go above 100. So it says for the first 3 hours the store is open, the store sells 20 cartons per hour. Now, I don't know about you guys, but when we sell cartons, does that mean it goes down? So for 3 hours, it's going to go down by 20. So 100 minus 20 is 80. Then we go down another 20, so that should be 60. Then we go down another 20, and that should be 40. So there, we covered the first 3 hours already by just going 20 down each time. That's our rate of change right there, right? Going down by 20 each time. Let's keep reading. Over the next 2 hours, no cartons of strawberries are sold. Man, no one wants any strawberries. So if I start at the latest green dot, I know that there will be no change for 2 hours. See where I put that blue dot? It's a flat line, no changing. Then it says the store then restocks 10 cartons each hour for the next 2 hours. So for the next 2 hours, it's going to go up by 10. So from 40, notice it's at the 40 mark, it's going to go up by 10 to 50, and then up by another 10 for next hour to 60. Finally, it says in the final hour that the store is open, 30 cartons are sold. Man, strawberries are the hot, or they're selling by pretty hotly, right? But for 30 in the next hour. So I'm at 60. I'm going to go down all the way to 30 right here. It drops down. Not because it sold 30 cartons, right? But 60 minus 30 is 30. Now that we have that, I'm just going to do this in one go, guys. I can connect all my dots, and we're done. So once again, notice how everything's like color-coded? I dealt with it one step at a time. You don't need to color code things, but I just wanted to show you that, so I showed you guys how I'm just pretty much cutting up a big problem into small little problems. If you have any questions, please stop by for office hours. But otherwise, you guys have a great time. Bye.